don't have ST4.
I don't have ST, but from but that, I mean, there's this, if you just say that we started with the unit square metric, not the unit square metric. What is nice is that in algebraic, you can make a clear distinction between these 4D metrics which satisfy their own existing equation. Like, the 4D sphere metric satisfies its own existing equation. Turns out superpositions take you out of that field.
Okay.
S4 had some metric and this can change and the metric changes.
That does not satisfy.
It doesn't have I mean, the changes that superpositions induce cannot be accounted by usually under according to Einstein equation, you can never reach something like that.
Good afternoon, everyone. I hope you've enjoyed your lunch. So we are all set to begin the second half of today's program. And I would like to invite Debangshu to continue telling us about modular theory and algebraic QFT. Over to you, Debangshu.
Yeah, thank you. So last time we essentially defined modular operator, modular conjugation, and we defined relative entropy and said that it has this particular positive definite structure. So today what we will be doing is we will be looking at a very concrete specific example, and what I will be doing is the example of a finite dimensional quantum mechanical system. Yes? Okay. We will be looking at a finite dimensional quantum mechanical system, and okay. So our starting point is a bipartite system with the Hilbert space structure. H1 tensor product H2. So since we are in quantum, I mean, as of now, in a finite dimensional quantum mechanical system, I can still have the product-like structure of the Hilbert space, and A is the algebra of operators on H1, and A prime is the algebra of operators on H2, and of course they are commutant of each other. They are all the elements commute. Now, as you can recall, a vector here in H is cyclic in H1 or in A if and only if it is separating in the commutant A prime. Okay. So now to write down the most generic state, so what one can do is one can start with of course the most generic decomposition. So this has a basis say some k and another being some k prime. You can use the singular value decomposition theorem, which is a pretty standard theorem in linear algebra, and essentially write this in what is known as split decomposed form, where you simply have this. These k and k prime are orthogonal unit vectors within H1 and H2 respectively. Also we start with all the ck's are non-zero. Okay. Now there is a flow of logic here, which is that, so if you so the first thing to notice is a operator which is within the algebra of A can be thought of as an operator A cross 1 which acts on the full Hilbert space H, right? So if this kind of an operator, if it annihilates psi, if this annihilates psi, so it will annihilate psi if it annihilates all the basis vectors in the first Hilbert space, right? So this essentially tells us that if K is the full basis, if it's a complete basis, if this set K is a complete basis, then essentially what this implies is psi is separating. Okay? Now the third point is, so essentially you see the way this the way this system is set up is H1 and H2, so these arguments are symmetric in within the Hilbert spaces H1 and H2. So also if K prime is a complete basis within the corresponding algebra A prime, I can also say that psi will be separating, right? So so both of them, so the statement is that psi is separating if and only if K is a complete basis in is complete in H1, whereas K prime, sorry, this is my notation, is complete in H2. Now,
can you explain how? So you're using that statement that psi is cyclic.
yeah, psi is something that belongs to the full Hilbert space.
Fine.
So this will be separating if and only if this is complete in both H1 and H2.
Okay. So yeah, using just a second.
All I am saying is that this A operator should annihilate all these elements, like all the basis vectors of both K as well as of both H1 and H2. That's
what
no. I mean this is the. I mean I started with this. Suppose there is an operator. It annihilates psi provided all of these happens. So this was my first.
Okay.
This is from where I started. A is some operator. If it annihilates, then this has to be.
Annihilates all K?
Yes, all K, all the basis vectors.
So by complete you mean it annihilates all?
Yes, yes. K is a complete basis of H1.
But that's trivial because you said it's symmetric composition and you can find a basis.
Yes, but the thing is that I mean it need not be that all CKs. I mean some CKs can be 0. I mean in those cases those elements will not even be there, right?
You can find a basis where CKs are not 0.
Yes, yes, I can always find that. I can always. I mean not just 0. I mean I can find a basis where it's always positive, right? So.
Just to understand, like, so H1 and H2 need not be the same dimension, or they have to be the same?
They have to be the same. I mean that is what I am going to. So these arguments, what it will tell you is that this object psi will be cyclic and separating. So using this also, what I mean the argument is, so now because now you see that this is separating in both of them. So you stand at H1. So you stand within the algebra A prime, and you say that it's cyclic in A, and then you go to A and you say that it's cyclic in A prime. So psi is cyclic and separating in both of them. That's the argument. That is essentially the argument.
Psi is separating if A acting on psi is 0 implies
A is 0.
So I don't see that statement.
How is second true?
Sorry?
I cannot see how second is true. A is some non-zero vector.
It has to be a statement about A, right?
Yes.
Annihilates everything.
So A, yeah, A annihilates all the basis vectors. So A has to be
Okay.
0.
All right.
But
Yeah.
I probably am confused with the first sentence. Like if it annihilates psi, it annihilates every K. Why is that?
Because I mean I'm writing it as if any arbitrary vector is an expansion in K.
Arbitrary vector. I thought we had one candidate psi we are focusing on.
No, this is a generic expansion, right?
I thought we are choosing some particular cyclic psi.
Yeah, I chose a generic vector. This is a generic vector within the Hilbert space.
If it annihilates,
If it annihilates psi,
So you're saying it annihilates every, if A annihilates every, so it's already generic.
yeah, this is the most generic vector that you can write, right? In H1 cross H2.
assuming H1 and H2 are the same, right?
Yeah, I mean they have to be the same dimension. But even if you, so this is how the argument works. If
How
you,
is that the most general state?
No, this see, okay, Smith decomposition does not require you to be, it need not be of the same dimension. It can be different dimension and also this will work. But what will not work is this, I mean, this argument. That will only work if both of them have the same dimension. So you can, okay, one thing you can do intuitively, you can think of it this way. So,
Before I don't understand the Smith decomposition part itself. Maybe that's where my confusion is. What exactly is the Smith decomposition?
Smith decomposition tells you, so suppose product these are basis vectors of H1, these are basis vectors of H2. Smith decomposition essentially, so this is sum over n comma n, tells you that you can find out some basis such that this thing can be written as okay, sorry. I should write here, sorry, CNM, right. Okay, this is what I start with, and what I can show is that this object is equivalent to Cn sum chi n prime. This is the statement. So there were two sums here. Now I can always write it in this way. In some case, I mean, essentially I can make sure that it's you think of it this way. These are like column vectors, these are like row vectors, and these states are n cross n matrices. Okay? And you can essentially diagonalize that matrix
So psi,
such that every
so is psi has to satisfy some properties for this to hold, or
no, this is generic.
But Cn is positive also.
Yeah, Cn has to be, yeah, that has to be the case. All the Cn will be non-negative, not positive. I mean, some of them can be 0 for generic this thing. So I started with a particular thing, a particular, so this is something which is generic. I have started with this absolute generic state. So this is my full Hilbert space, and now I am saying that if this operator annihilates psi, then it has to annihilate every vector key.
That's only possible if Cn, none of the Cn's are 0.
Yes. Right? So now,
Something like a maximally entangled state.
this is not, you should call this fully entangled or completely. A maximally entangled would happen if all of them are equal.
Yeah.
Right?
Something like.
It is not that. Fully entangled is, okay. I don't think fully entangled is the right word. I think in literature it's called completely entangled.
Okay.
Completely entangled is different from maximally entangled. Maximally entangled means quite literally S can be maximum value, right?
So one question, in the second equation of this side, what elements does n run over?
That dimension, the dimension of the smaller one. So in principle, yeah, these two things can be different. So, yeah. Okay. So by the way, these answers. So you asked, can there be only one particular cyclic and separating vector? So I just showed that anything like this for a finite dimensional case is cyclic and separating in the full Hilbert space. Okay? Yes. So see, the point is, again, this mid decomposition originally, because to build up this argument, we started with something generically with different dimension, but what this tells you is that if you want to have, what this tells you is that this thing is cyclic separating only provided both the dimensions are same. This sort of gives you the idea that probably, subsequently we will see that you can think of these two to be dual of each other, and that is how we should be interpreting it. It's no, I used this. We showed last time. Suchetan also showed this.
In this argument, right, you proved something here.
Yeah. Yeah. So if it is separating in H1, it will be cyclic in H2, and if it is separating in H2, it will be cyclic in H1.
So you proved something is separating, right? Something.
Yes. And then you use this.
That you didn't use it as cyclic.
No. That was separability. Then I use this.
So finite dimension, everything is separating is what you proved.
Yes. And then, but then in this double copy, I use this. Henceforth, everything has to be cyclic and separating. That's the argument. Okay?
When you write it as CN, you said that this is like diagonalizing.
Yeah, I mean that was the kind of, I was asking you to think of this as column vectors and think of these as row vectors. Okay? So what you have, your states now are n cross n matrices, and these things are sitting exactly on the diagonal, right?
So n cross n, that means square matrix, so both dimensions.
Yeah, dimensions are equal. Now I am assuming, because I mean we can move away from the non-equal dimensionality. Let's just focus entirely on this. So that is what it means.
Where did you prove both ends are same? Both the dimensions are same? How did you get that?
So okay, that will follow because so yeah, it will not form a complete basis basically. For completeness of basis, you require that. I mean, both ends has to be the same. See, if I mean, there is one other way of thinking at it is that suppose they were not the same, then essentially in this when you write down this psi, you will have some n cross m object, and there will be a bunch of zeros that you will be forced to put, right? So that's what the problem is, and in that case, yeah. Yes, you initially started with something non-equal dimension, and what you see is that if this state is cyclic separating, see, if this state has to be cyclic separating, then what you see is that both of them have to be the same dimension. You think of it, you need not go through this argument. What you can do is, you can start with one single Hilbert space H1. You want to go to a purified state. You just create the double copy, and you don't need to, you can just completely bypass this, and you can directly show that for this purified state, any arbitrary purified state is cyclic and separating. You can think of it that way also. Okay? Okay, so now let me move this there. What?
In case of ABS both-sided black hole, internal black hole,
Okay.
that state that thermodouble state or
Thermophile double. Yeah, this is exactly. Yeah, this is the same. I mean, thermophile double. It's the same thing. There you do for generic for a thermal system. Here it's a more generic setup. Oh. So our goal is to find modular operator in this system. I have to find S of psi. That's what I want to do. Okay, this follows from definition that.
Can you pull the other board and write on that?
Oh. You mean this one? Okay. Okay. So this follows from definition of our Tomita operator from last time, if you recall, right? Now, I have this bunch of numbers. Pick out any two of them. Pick out I and j. Now, I am defining the action of this operator A on the state I as equal to j, and A acting on these other states is 0 if k is not equal to I. So, what this immediately tells is how the adjoint is going to operate. Which is this, and also this is how I define action of my adjoint and the operator if this is k is not equal to j. So in some sense the job of this is to take I to j, and A dagger's job is to take j to I, essentially flip them. So the action now on S of psi, so this acting on a generic psi gives you Cij comma I, right? So it's just that
I missed, are your IJs are this 1 to n is the
basis, yeah. I'm just labeling by the numbers 1 to n, and I have chosen. This is how I have defined the action of my operators, A and A dagger.
A is such that this happens.
Yeah, A is such that this happens. I'm trying to determine what is S of psi. No, I should not say this is implied. This is the action of A and its adjoint. Okay. So, okay. What this tells you is, or rather I should okay. So from this particular action of S of psi, what we essentially get is action of S psi on j comma I sorry, this will flip, and S psi dagger acting on I comma j will be j comma I. So this is what the action of S psi and S psi dagger will be. Now these are just generic any arbitrary basis in the full Hilbert space. So what you have here is a complete description of how S psi will act on any arbitrary state of HAB.
How was psi?
Sorry?
Like, what was psi? I mean, in terms of IJ.
The state that I wrote. So psi is
That one.
yeah, psi is sum over Ci I comma j. Kind of I prime basically, sum over all I Ci I prime. This is what it is. Actually, I should not use I, because I's are some specific these things. So I've been using k. Yeah, this is the summed over index. I have chosen two particular I and j, and this is what I am doing. I and j are some fixed thing that you have chosen. Yeah.
And okay, fine.
Yeah. Okay. So this was psi. This is actinoid, and this is what I have got. So again, we derived a huge bunch of algebraic relationships connecting S, S dagger, deltas, and J's. We did this last time, and from all of that, what you can show. So delta was basically S dagger S, if you recall, and what you can show is that and the action of this modular conjugation operator is to essentially okay.
So I have one question. So is the action of A and A dagger on the states, is that unique?
Sorry, action of
As in like.
yeah, see this is always unique, because if you recall, Riechleider theorem tells you that this A acting on psi has it's going to produce a dense set, and this is an unbounded operator acting on this dense set, and there is a theorem again in linear algebra which will tell you that this is always unique. So this there is no, once you have chosen that this will be the action of A, this will always follow. Okay. Okay. So now what you can do is, you see, I and j are something very specific. I have chosen them by hand, quite literally. So what I can do is I can adjust these phases in these coefficients such that I make sure that this object sitting in front is always 1. It's very simple to do. I am simply going to choose Cj as I pi times Cj bar, and correspondingly Ci I will choose as e to the power minus I pi. I mean, the phases will be just opposite of each other so that they cancel out, and this just gives me 1. So no, this Cj by Ci bar. So this is also Cj by Ci bar, but this flips. S dagger.
Like there is some steps you know.
Yeah, this is just you have to use delta is equal to S dagger S.
Delta equal.
S dagger S. It will follow. It's a short. It's not even a yeah. Okay, so
No, not about delta. About S. S.
yeah, I mean you can just use this definition. It will follow from the definition,
Yeah.
right? This you want to know how
Yeah, A is identity there, right? Identity cross identity. So it will just give same thing back.
A is not identity. A is this operator. You have to act it on.
But Si, when you act on Ji,
Yeah. A is acting on psi,
this is fine.
right? This is fine.
Lower on
A acting on psi will give you,
that is fine. Second line.
it kills everything else, so it will give you Ci, I.
Yeah, that
I have just put Ci here. I mean, so
from here.
this will give you Ci. Now Si acting on Ci means Ci times identity, so you use that and
Okay, fine.
I mean,
Fine.
you see, right?
Yeah, fine.
Okay. Phi is another. Dagger alpha is I. So now this is how I am defining my action of A and A dagger. So the reason for doing this is basically nothing but because I want to define how
Second step is side dagger acting on IJ.
yeah
Should be Ci by Cj bar.
C this coefficient. Do you say that?
Next step.
1 second. So I'm going to act this with S dagger. Oh, you're right. Yeah, you're right. So the thing that you need to do is act here on both sides with S dagger. So now you will get S dagger acting on Ij, but S dagger psi S is identity. So on this side you have J comma I, right? And then you have to shift this. I mean, this is the thing. This is the reason why Pawan is saying this will be C bar I by Cj. Okay. Sorry. Oh no. It will not be, because this side these things are I and J. Do you see what I'm saying?
Yes.
It was fine. It was fine. Sorry. This will be I and J. You didn't understand.
Can you explain like how you are getting the bar in the first?
In this equation? Okay. Ci is acting on psi. Okay.
S square is identity.
Sorry. Just a moment. Let me just. I mean, in this case, it will be, because you see, it's, I started, okay, just a moment. Let me first explain this. So when A acts on this, it's fine, right? You use this and this follows from. Sorry. Okay. Sorry, how to get to this? So when I'm dealing with maximally entangled state, which I can choose to deal with, that is also cyclic and separable. In that case, all my CIs will be equal, and what happens is this modular operator becomes identity. So in that case, you can see here, S dagger S will be, but S dagger S is, as you know, it's delta. So I'm just trying to think of, again, this is one of those little algebra things you need to use some identity to get from S to S dagger. But yeah, that, and also, you know, this flipping needs to be done, and you will essentially end up with this. In any case, I can tell you maybe later. This is some really minor algebra. Should not be a problem. If it is fine with everyone, I can. So this is exactly how I am going to define when I have another state phi. This is how the action is on of this operator A, and this helps us in defining the relative modular Hamiltonian. The relative Tomita operator, which is this turns out to be d alpha by c alpha, I alpha, and this is very similar to the relations that you will obtain for this case also. This is what you obtain. Also, one thing is that I'm choosing this to be my unit vectors. So what this essentially tells me is sum over Ci is sum over d alpha equal to identity. Okay. Now, this entire story could be described by density matrices also, because we are in a finite dimensional setup, and what we can do is, so rho 1 2 is the density matrix associated with the full Hilbert space, right? With the state psi in the full Hilbert space, you trace over any one of them, which is in this case 2, and this is my rho 1, and rho 2 similarly is this, where rho 1 2 is psi psi. Now, similarly for phi also, we can associate it with a density matrix sigma 1 2, and exactly like rho, it will also have sigma 1 and sigma 2 as reduced density matrices when you trace over subsystem 2 and subsystem 1. Okay. Now note that so rho 1, this object, okay, let me.
Over there, that's your final result for delta and j, right?
Yes, this is the final result for.
So what do you say that for completely entangled state you can find delta and j of such sort?
For completely entangled state, these coefficients will be 1.
Complete or maximum?
Oh, sorry, completely entangled state, yeah, these things will be there. What I said was that I can choose my phases appropriately. So I will choose such that this will become 1, Cj by Cj bar. I can always tune it that way. I and j are some very specific vectors within a set of basis vectors, right? So I will choose Cj such that this is 1. Okay.
All right.
Okay. So for psi, what you see is this simply becomes this. So this is the expression for ρ1 and ρ2. Now notice that so now what you have done is essentially written these states in the full Hilbert space as matrices where these CIs are, mod CI squares are sitting along the diagonal. So this object will be invertible provided if every one of these CIs are non-zero, which is what our original assumption was regarding the state psi. So finally,
Why do you want it to be invertible?
you'll see what exactly why it is needed. So now all you have to do is essentially compare these two objects. I have written down the expression here. Delta psi is, yes, so this is my expression for delta psi, right? And these are my expressions for ρ1 and ρ2. Oh, sorry. Of course. Yeah. So these are my expressions for ρ1 and ρ2. And this is the expression that I have for delta psi. So using these three, what one can see is that this delta psi is nothing but ρ1 tensor product ρ2 inverse. Right? I mean, all you have to do is you have to add this on some generic state of, so sum this over say m. I should be sandwiching them actually. ρ2 inverse is essentially nothing but 1 by Ci square, or rather, yeah. Sorry?
Can you repeat the statement? ρ1 and ρ2 C1, Ci are not 0? What did you want?
Then it is invertible. That is precisely because I need these Cj's in the denominator. This answers your question, right? So you can see here that, right? So you can simply compare these two expressions and see that this coefficient is exactly what you have here, Ci mod Ci square by mod Cj square. So this is, yes?
That expression of delta psi, the action what I have given,
Yes?
that is true for the particular choice of A.
For, yes, so I define A this way, but the thing is that my Tomita operator, this has to be, so this and this, these two dictates all the subsequent step. Now this object needs to be true for any operator A. So I am just choosing one of them and I am trying to derive, right?
And that equation is true for this particular choice of A.
Yes, yes.
This is true for
No, this equation is not true for this particular choice A.
No, not that one. The delta psi acting on J,
Yes, for this particular choice.
that you are getting this delta psi.
Yes, yes.
Then isn't it dependent on the choice of A?
It's not dependent on choice of A. It's not dependent on choice of A. Rather,
Try other A's later.
sorry.
If you, that's once you go into Si on J and I, it's no longer dependent. That's
Yeah,
true
it-
for any J and I.
This
That
this
required you to get to that, right? You can change now I and J to anything else.
yeah. What I have shown, I mean, this is one specific example of A that you choose explicitly to look at this. But once you reach this equation, because this is something which is generically true. This is true for any arbitrary element in the basis vector, right? This is some generic element in the basis of full H A cross B, right? I mean, you then have to define the adjoint and etc. appropriately, right?
Will you get at the same result?
So that's the thing. Once you choose the action of A, you see you need to define this object appropriately, which will actually, I mean, it will make sure that this thing is consistent. You see, there is a dagger that appears here also. So if you do choose some other A, then you need to define this action properly.
Let's say I choose some AI which takes me to J plus K.
Okay.
Some other K. Will I get the similar equation?
So firstly, there are problems with the definition that you just gave. So your K has to be defined the right way so that it's not greater than n, etc., etc. So you need to now define for me a dagger, which should also be appropriate enough. And if you indeed do that analysis, you should get the same thing. You should end up with this.
Anyway,
That's the statement.
so at the end you'll get something.
Yes.
Could you apply that S on some A psi to show that it's arbitrary A?
Yes. For arbitrary A also this will work. That also you can show. Here I am choosing a specific simple example because you see, once you have given me A, it does not just, I mean, you need to define this object also appropriately. That's the thing, and that fixes the right hand side. So it's a pretty constraining thing.
When you started to introduce this new AI equals to alpha, I thought you were going for the relative terms of it.
Yeah, I'm writing the relative. Just hold on. This is the expression. So here are the d alphas divided by the c alphas. So rho 2 inverse again will be, so this is the denominator that comes in. So you compare it with this expression. I have not written down the expression for sigma 1. So if you consider this, you will end up with this, right? Okay, now
Do you have reference for this?
Witten's notes.
He has done this example?
Yeah. This example is explicitly worked out.
Nice.
Okay, I think section 4. I think he has explicitly 3 or 4, one of these. Okay, so you see, in quantum field theory, algebras are generally associated with space-time regions. I am not doing that. I am doing a finite dimensional case. So here we don't have that luxury. But still, what one can do is one can use the definition that was given by Araki and just try to see what one gets in this case. So if you do this, we have just seen this is nothing but a trace over the full Hilbert space. So this is trace over 1 and 2. And from here, you see that you use this expression for delta psi given phi. You simply plug it in, and now, once you do this, you see here when you are taking trace, so first you take a trace in this object over subsystem 2, right? So once you take the trace over subsystem 2, it's trivial, right? There is just identity sitting here. It's not going to do anything. So here you have trace 1, rho 1, log sigma 1, minus here in this case, you have to trace over the first one because this is the trivial part. So here you are going to write trace 2 Now this is the point which I was telling Anish about, that you have to make the identification that this H1 and H2 are duals of each other. Because then, I mean that's the most natural thing to do Because precisely of the action of this operator j psi on j comma I, what it does, it changes j to I and I to j. In some sense, it takes a row vector, makes it column, and takes the row, and vice versa, basically. So, so what it does here, it ensures if they are duals of each other. So what this means is, you are essentially dealing with a second copy of the same system, right? So these two must be equal. If that is the case, this finally boils down to why do I need to take a star of row 2? This is a trace. So you have a double copy, you have the same system twice, and trace over, I mean, this is trace 1 of row.
You think of some kets as stars, no?
Huh?
You're saying you can think of the kets in the.
But now it's in row. I mean, I have already, these are like matrices, n cross n matrices. This is a partial trace that I am doing.
So to define this relative entropy, you need double copy.
Yeah, in this case, yes, that is how this entire machinery is set up.
I mean, a dual is, it's a Hilbert space, so dual is isomorphic.
Right.
A trace, that one, you can replace 2 with 1.
Yeah. Sorry, I have missed a sign here. So this is minus. So this is going to be minus. This is going to be plus. And so this is going to be trace rho 1. This is the standard definition of relative entropy that you probably have encountered in standard literature of non-relativistic quantum mechanics, which indeed, and this was actually the original motivation. This gels nicely and dovetails nicely with this particular formula that is there for generic QFTs. Now, it does not go to, see, this is trace over 1 of rho 1 log rho 1. This has to be equal to this because it's the same system, just twice. I mean, if you consider, I mean, look at this object. Rho 1 and rho 2 are essentially the same thing, right? This is it's conjugate of each other. You should think of it that way. Okay. Now, the next thing that
Where is this identity in outcome? Can you explain that step again?
which one?
The step before to that.
Log of this, the log first hits this times identity, then there is a minus sign coming because of rho 2 to the power minus 1, then it's first one, then log hits the second one. That's how the log works on a tensor product kind of a structure. Okay, that is how we are getting this.
That equation that you had, rho 1 equals to and rho 2, where you
Which one?
not equals to, I mean, rho 1 is that over on that board.
Yeah.
So there isn't this true for any row 1, 2. This will work, right? So
Which?
you have H equals to HA cross HB.
No, if
It will be the same.
if B is different, then no, of course.
No, same dimension.
Yeah, same dimension, everything. Yes, yes.
The properties will be the same.
Yeah, I mean if the same state, yes.
No,
That's-
psi is the pure state, and you're taking the trace.
Yes.
You will get same probabilities on both sides.
Yes, yes. That is essentially that statement,
So
right?
you don't need some assumption or double copy, right? It'll
No, but I mean, my system is set up like that, right? I am dealing with H1 cross H2, psi, all these things that you see, they are states in the full Hilbert space. I have to purify my state. Without that, I cannot do this. The purification is necessary, right?
I mean, yeah, maybe it's the same thing as what I'm saying and you're saying.
Yeah.
Maybe they're the same thing, but to me it seemed like this was somewhat unphysical. But
No, there is nothing unphysical about it.
okay.
There is nothing unphysical about it. you have to define this.
It seemed that you're adding by hand some double, so you have a system A. And
That is how you purify something, right? You do the.
that's true. But I could have also have had a general Hilbert space of 4 qubits. I split into 2 and 2 as the.
Yeah. So what you are doing is, I mean, you are doing the reverse thing.
Yeah.
But you are saying that, look, I mean, this 2 qubit thing is what I'm going to call H1. The other 2 qubit is the second copy of H1. So
your 2 qubits, you're demanding that the other
Has-
has same dimension. So there's
yeah, it's dual. So think of the first one. The Hilbert space elements are row vectors. So you should think of it that way, and that is the right way to think. And this Hilbert space of H2, which is also 2 qubits, it's the same vectors, but now written as row vectors. Now you are multiplying them, right? This is the Shubhai, is this clear? Why? Oh, I mean, the elements of H1 are row vectors, and H2 are H1 are column vectors, H2 are row vectors, but they are essentially the same vectors. And now you are taking a tensor product to create size which are part of the full Hilbert space. That's the physical picture that should be in your mind. Okay. So from yesterday, if you recall, what we saw is this, and from what we have derived just now, the explicit formula for at least finite dimensional systems so delta psi to the power is exactly same as this object. Okay. So for any A which belongs to the full algebra of A and B, what one can say is right, because one of them, the rho 2 part in one of them is going to come with a factor of plus is, another will come with a factor of minus is. They are going to mutually cancel because this operator A is only going to affect the first sector. So what you are left with is just things in the second sector. But look, this is nothing but this is of the form B cross identity. Now B were part of your algebra which were operating on the first Hilbert space. So what this does is, more generically, people write it this way: acting with such unitary modular operators sends A to A. This is what is known as the automorphism, the modular automorphism. Okay? So for the relative modular group though, that we see something nice, which is that if you consider this object, this turns out to be this is what it turns out to be, and that also you can see exactly from this formula, because again the rho 2 inverse part is going to mutually cancel out each other. One comes with a factor of plus is minus is, and what you are going to left you will be simply left with this. Now if you look at this object, there is something nice. This sigma 1 were reduced density matrices that were associated with the state phi. The right hand side does not care about the original cyclic separating state that we started with, which is psi. So here what you see is this process that we did with deltas, it is known as conjugation. So, conjugation with delta does not depend on psi. What this implies is essentially what is implies is this statement, where psi prime is another cyclic separating state, and as we know from our previous example, there are many cyclic separating states that I can choose. This is true. This object does not care about, as long as this object is cyclic and separating, it does not care about what you place here, right? Psi prime is another cyclic separating state. I mean, this equation says that everything here on the right hand side, this is sigma 1, this is reduced density matrix associated with phi, not with psi. So the right hand side does not care about what this psi was. All it cares about is, in this derivation, the only thing that we have used is the fact that the psi has to be cyclic separating, or else this object is not defined, right? Because if you recall, S was acting on A of psi, and A of psi was a density.
But this also closes, stays within the algebra.
What do you mean by?
There is a relative modular operator.
Yeah, we just showed that this will always be within this algebra.
That's fine, but this is the relative one, right?
Yeah.
Still it's-
Yes. So, I mean, you can see it from here itself, right?
Yeah.
This is within the full Hilbert space. Huh?
In QFT, it may be, I don't know about that.
No, in QFT also. So, all these statements that I am making, by the way, at this level, forget about how we derived it. This statement is, by the way, the central theorem of Tomita-Takesaki theory. This one and this one. These two things are the central statement of Tomita-Takesaki theory, the main theorems, and what this tells you is that conjugation by operators of this form, where delta is a modular operator, does not care about whether this is the case. In the context of holography, this statement will pop up as the fact that your bulk relative entropy is exactly same as boundary relative entropy, which I don't know, I mean, if you will probably talk about it at some point. Yeah. Okay. Now. Yeah. Okay. So sometimes, yeah, it's just that operators, sometimes I put a hat. Okay. So actually, to tell you more, for generic QFTs, these two theorems that I just showed, for generic QFTs, it's very difficult to prove. So what the way people prove it is they quite literally start with such, huh? They start with an algebra A1, which is a 2 cross 2 density matrix, and then they go to 4 and so on and so forth till, I mean, basically you have 2 to the power n cross 2 to the power n algebras, and all these statements that you see in QFT, they are proven as a limiting case of these matrix algebras. That is the proof that exists as of now. Of course, the goal is to. No, you can't. I'll come to that. But even without, I mean, you will see that even without that assumption, so, I mean, you can reach results like that. Just give it. I mean, just wait. I will come to that. Yes.
No, this is an algebra. You don't need to factorize it. There's no factorization.
No, but
Hilbert space factorization is the problem, but on the level of algebra, there's no question of factorization.
yeah, but these theorems that I just proved, I started with a factor. I mean, I started with H1 cross H2, right? So that is what.
He's probably saying like the sequence is made on algebras, not on Hilbert space.
Right. Yeah.
No,
That is
Algebra is defined as
I mean that is also true.
of the Hilbert. So this A1 is the bounded operator on H1, right? So then A2 is bounded operator on H1.
But it is true for each of those algebras.
So
Because they can be
he is describing the current state of the art group, no? So in the limit, so that's done on algebras of this sort. So you increase the as I understood, he is increasing the size of the Hilbert space and therefore the size of the algebra.
Yeah, the belief is that if you go sufficiently high, I mean,
But in Hilbert space, there's no sequence because this is a factorized sequence at every step, but at the limit you have a QFT which is not factorized.
this is what is essentially happening. And in some sense, again, you are going to ask that, what do you mean by subalgebra? Fundamentally, when you are talking about non-relativistic quantum mechanics, your Hilbert space that acts on A is typically smaller in size than that acts on the full system. But there is a way you can do some embedding and you can define a nice, so you can think of it as a subalgebra. And this is how you should think of it. Essentially, the physical statement is that in QFT, any bounded region U should be thought of as a very large number of qubits. And that is how you should perform the analysis. That's the physical statement. What we are interested in is, sorry, I have to write here, right? Okay, what is the question? Okay, question we are trying to answer is, now what is the action of this modular operator on a generic state? Psi is a separating cyclic state. This creates all possible states in Hilbert space. I want to
Lighted board.
Can you show the previous 2 seconds?
this one. Okay. Point 1, the first thing to note is this object has finite norm. So the way to go about this is, so you need this relationship along with the fact that its psi dagger S is delta. All you have to do is you need to perform some manipulations. So what is going to happen is, remember that delta psi, this was Hermitian. So you can take this outside here and simply replace this delta psi with S dagger S. Should I do this? Should I? Okay, maybe. So what you see from here is that okay, is the notation clear, by the way? So if you have an operator A, x and y are some states, what I am essentially doing is I am writing this object like this. Okay, it's as if I am computing the inner product between the state Ax and y. That's how you should think of it, and that's why I am writing here Ax. Okay. This is the notation that I have used. So when I get this out, what I have is delta psi half dagger, but this is Hermitian. Okay. Now delta psi is S dagger S. But remember that S was an antilinear operator. And for antilinear operators, by definition, the action of adjoints is this. You do the same thing, but you have to take a complex conjugate, antilinear, to compensate it. Okay. Right? That was by definition. If you recall, if W was an antilinear operator, this was how it was defined. Okay?
Yeah, correct.
And that gives you this. But Tommy, no, okay. You should not put the bar here.
No, the bar has already been taken care of.
Yeah, I have taken care of the bar and then written this. I mean, if you want.
The adjoint comes on that side, but
Yeah, I mean, generally that's how it's defined. This is what it is. This is, I mean, you use that for antilinear operator. This is the case, and all that I have done is I have simply used that. Think of S dagger as W, S psi A psi as lambda, and this object as chi. You can write this, right? But this is nothing but. I mean, this is how we define Tomita operators. S exactly. So. But these were part of your Hilbert space. These were, you originally started with something bounded and nice vectors. So this is finite norm. Okay? Huh?
yeah, it's actually a square. You have to take square on the left side.
Oh.
But that's really matter.
Hi. Sorry. Yeah. Okay. Okay. Now, another important inequality that we require is, so I want to do this part. So what I'm going to demonstrate. So this thing. Okay, let me get there and then I will maybe talk in some details about it. So for every positive real number, this relationship is true provided R is within this boundary, between 0 to 1. Okay? If that is the case, in the context of operators, what we can write is, because you see these are positive definite Hermitian matrices, this can be generalized like this. And now, yeah. So whenever I am writing things like this, always at the back of your mind, think that there are chi's sitting on both sides. Okay? So, I mean that's the meaning of. Using this equality and from what we just saw, with a very similar kind of manipulations, you can show that this object also has finite norm. Okay? Now, note that the lambda to the power is operator, this is unitary. So, this implies this object, which is delta psi is, this also has the same norm, because this is a unitary operator, it does nothing to the norm, it does not change it. So if this has finite norm, this better also have finite norm. For
Why is this unitary? It's
delta psi to the power is.
It's Hermitian operator raised to some power.
Log delta is
Log.
Log, okay.
I mean, you take a dagger of this, you're going to, this I is going to become minus IS, and this thing times this will be identity, right? This is what is, so, okay. No, I should, for, this is important. Or else it's not unitary, right? Okay. So, so what this means is, now if I suppose so all of these arguments basically tells me if I now define a Z as S minus IR by 2, if this is how I define it, then this tells me this object A psi is well defined when imaginary part of Z is less 0 minus half. Okay? Right? I mean, R by 2 is the imaginary part, that's why this factor of half. Remember, all of this was true provided when we restricted ourselves to this window. Right? So this basically gives me this. So this is the region within which this object is holomorphic, nice, continuous, etc. Now, if I had two operators, A and B belonging to the algebra, I define a function Now I am looking at objects like this. This is the function that I am going to study, where A and B are part of the algebra A. Okay? Now, the first thing is we make Z complex. Now, what we have seen is that as long as my R is less than equal to 1, all of these states that we have got, these states are normalizable, right?
You have to put R by 2? S minus 1.
I mean, I can always choose to have. R is, I mean, that's just a matter of convention. Yeah, I mean, there I have put R by 2, yes. I mean, here I am just using R. I can always do that. I mean, all that will do is it will, instead of imaginary part of minus half, in this case I will get, so this is well defined when, that's all the change that will, right? Will be,
Any need to change it?
huh?
I mean,
Sorry?
any need to change it?
No, imaginary part of Z now is just R, not R by 2.
Yeah, agreed, but same notate, I mean,
Sorry?
I mean, any specific need of changing that, that's
No, there is no specific need of changing that. I mean, okay, fine.
yeah, just what I'm
Is this fine?
yeah.
No, R by 2 or R, imaginary part of Z is imaginary part of Z. That you can't change to minus 1 and half. It should be always minus half. But you can change the range of R from 0 to 1 to 0 to half or something. If you write R instead of R by 2.
No.
That's what you meant.
I'm going to start with this R, right?
Then it's
This is my R. My R and Z has to be related in a certain way. The way Z is related to R is not the same in this equation and in this. So how can they be the same?
but the imaginary
The-
part of Z is invariant of what you call him R or R by 2 or whatever it is. That's
Oh, okay. Yeah.
that there you can't
Yeah, I mean the reason, there is no need for change, but yeah. I mean, I have written that in my notes, so if it's fine, I can continue with. So, okay. So,
do you mean you're taking a
inner product of two such states. That's why you have the imaginary part to be double or something. Is that what you meant? Maybe that's what.
No, I mean, Z is this object.
There is a state. So
yeah.
the state, if you put delta power IZ,
Ye-
it's good enough. It's good. As long
Yeah,
as
this entire thing I am calling IZ.
right. For a state, it should be between -12 and 0. Now I guess you're taking the inner product of two such nice
Yes,
states.
yes.
Hence the imaginary part is between.
It's between, yes.
Okay, then I guess like yeah.
Because see, now there are not one operator, there's two operators, right? A and B.
Sorry. So then it's -1 I guess.
Yeah.
Yeah, that's what you meant. Yeah.
What?
Yeah, okay, then it's clear. Okay, thanks. Sorry, my mistake. No comments at all.
Okay. Sorry, where was I? So the claim is that Fz is fine, well defined, continuous, holomorphic, etc. in this range. Now, let me now look at the two extremities here. Okay. So first, so forget Z now. I am going to choose, because two extremity means first I am going to sit at r equal to 0. Okay. Imaginary part of Z I am just going to remove. I am first at this extremity. Okay. If that is the case, then Z is simply S. It's a real number. Fine. And then and on the lower boundary, when imaginary part is -1, this is basically a function of Z plus S plus I, right? This object turns out to be okay. Now, for a finite dimensional system, which we actually, sorry, what is the, yeah, so
F is not really defined. Well, why?
no,
In the f of S plus I,
yes.
A comes first, but in f of S, B came first.
Oh, okay, yeah. So there is a way you can prove this. Should I go through it?
Yes.
Okay. It's a bit of a manipulation that you have to do. So this is fine. I've just simply, okay. Sorry. No. It's R is -1. So S plus I. Right?
But you write f of s plus I. So that will make it -1. According to your argument.
Yeah.
-I, -1 is what they're saying. So it is delta over -1 plus IS. Yeah, fine. No.
Sorry, hold on.
In f of s equation, the term was,
Yes.
if we just put s plus 1, s plus I, then we I
Oh.
square.
Sorry, then probably I should write this. Minus, yeah. This is fine. This one is fine. Yeah.
Imaginary part Z equal to -1.
Yes.
So that means Z will be S plus I.
Yes.
So, but you are writing f of S minus I. No. Z is S minus I. Now put Z to be S minus I and evaluate f of S. You get f of S minus I
This is fine, right? All I have done is, this is a function of z. I have plugged in here s plus I. I have chosen r to be minus 1. Sorry, r is 1. Yeah. Okay? This is fine. Now, this object was Hermitian. So, okay. So, I have taken this delta half B dagger I have shifted here. This is fine. Now, this object I am using one of the relations that I wrote yesterday between delta j and s. Delta psi to the power half is nothing but this, right? I mean, this is from polar decomposition. S was j times delta to the power half, and j square was identity, right? So Js, j square goes here, delta. That's all I have been done. Okay. Now, if this is the case, remember j and delta psi to the power I is commuted. So, what I have here is j psi yes, okay. So here one more thing that has gone in is the definition also of S of, I mean, that is why this has become A dagger. SI, A psi has acted on it, and this has given you A dagger psi. Okay, that's why this has become dagger, and similarly B dagger has become B. Okay. This is this, fine. J is here. J and this object commuted, so I can change. Yeah, I wrote it somewhere. There, I think, yeah, here. It's commutes. So there are two things that I am doing. Okay. Now, because J psi is anti-unitary, there is a way in which anti-unitary, I mean, that also I wrote some time back, and okay. So, if you recall the way anti-unitaries chi and say lambda, this would be simply chi lambda. Okay, sorry, lambda chi, not chi lambda. This would be just this. And that is what has been used here, and this has finally given this. So this is how A and B has flipped. It just requires a few lines of manipulation, but this is how one gets this result. Okay? Does that? Okay. Which last step?
Which is equality of the two?
This I took there on this side.
All right. So you started with the A and B. No. You started with B and A. Oh, perfect.
I started with this and I showed this.
Yes.
This is this.
Yeah.
Okay.
This has some very nice analysis of this Penrose diagram and how things work.
Just can you hold on? I won't go there in too details. I'm just going to motivate basically the question that Sitendra asked me.
Do also people do such algebraic things corresponding to these extended weirder Penrose diagrams where there are multiple copies and so on? Like say some charged or rotating diagrams.
I'm not aware of, but
This is some analog of all these constraints there.
so the person who has been mostly driving this program are people like Nima Lashkari, Hong Liu, etc. I have not seen any of their works actually that talks about anything like this. I mean, they of course try to connect it with holography. The JLMS thing is a bit different. It's not this kind of, I mean, they don't do this algebraic QFT modular flow. I mean, they use it in a different sense, in the way that, so they are sitting in the Rindler wedge. They are already in a nice patch in a very simplistic setting.
But for algebras which has these, for Penrose diagrams at least which has these nicer extensions which are complicated and more.
I have not seen anything other than Rindler-like systems, honestly, for QFT, because it's generally like, you can understand, right? Tracing out is not a partial trace is not an easy thing to do in QFT. For Rindler, it works out nicely.
I'm saying, okay, maybe I can phrase it like this, like algebras corresponding to the causal wedges in these weirder diagrams is
No, I can't. Not to my knowledge, I have not seen them. Like say,
probably talking,
what he's trying to say is, think of something like charge Reisner-Nordstrom.
you have to say the diagram thing.
Yeah, I mean, you have essentially something like this, right? This would be one example. So this continues up and down for charge Reisner-Nordstrom, and what Akhil is asking is that has anybody studied algebras, etc., in various causal patches of these kind of Penrose diagrams? And derive these kind of statements. I'm not actually aware of anything. I mean, I have not seen, not to my knowledge. I can look up more and then let you know. Maybe.
It goes inside the black hole. Not the other black hole. It goes inside the black hole, but not to the other black holes.
See, eternal these kind of two-sided, these are very nice settings. These are very nice systems to work with. You see, yeah, you cannot. Yeah, for more, Akhil's question is for more complicated systems. I don't know.
Why should theory change?
What?
I mean,
Why should theory change?
yeah, I mean, you are doing some.
No, the theory does not change. The theory does not change, but you need to derive an expression. To compute something, you need to have an expression for the modular Hamiltonian and the modular operator. Like for example, for a finite dimension, I wrote this object. By the way, when I derive the expression for relative entropy, I have used these expressions. There is no way I could have connected this to this without this. I mean, otherwise everything is very abstract, right? I'm doing some operator, some
concrete settings. That's
yeah. So this is a formalism. The point of this formalism is this formalism should work from quantum mechanical systems all the way to QFT. And this is the reason why this is so difficult, because you want to give in one shot capture the effect of local physics of anything like this, starting from a 2-qubit system all the way to lambda 5 theory on Minkowski space. You would like to explain everything. And doing that requires, that is the reason for this formalism, but at the same point of time, the drawback is if you actually want to compute things, it's significantly difficult. I've forgotten, was this the board I was writing in? So, I mean, can I rub this? That's what I want to know. Okay, so for finite dimensional cases, we had factorizability, and the algebra A acts only on the first factor. Okay, and rho 1 is defined as the reduced density matrix by taking trace of over 2. This object, so this thing you define as e to the power minus k. The operator k is what you define as your modular Hamiltonian. So for the time being, I am going to put this word in quotations. Now, if you notice, in the definition of f of z, here, I could have made a replacement. What I could have done is, I could have as well defined f of z sorry, this is B, this is, what is the, power, I could have done this change also. So all I have done is I have put in one more unitary factor here. None of these arguments would have changed, and what this basically tells me, and I can do this, the reason is because del psi acting on psi is nothing but psi. So if you use this, fz can also be equal to this, right? Now if this is the case, what you immediately see is this object acting on psi, so this sort of conjugation of A acting on psi, this is nothing but this is this. Now further, what you know is that for any generic operator O, I can write it as, if I know my density matrix, I can write it as trace of rho times O. But rho has been already defined as e to the power minus k here. So f of z essentially becomes trace over states of h1 e to the power minus k, which is precisely rho, times b e to the power minus I zk a e to the power I zk. So this is the generic definition of f of z. Specifically, the two things that we defined, f of s, this happens to be and f of s minus I happens to be trace I got because I have this, right? It's between psi and psi. Okay. So trace of this object is nothing but, so call this entire thing O, trace of rho O. Rho is e to the power minus k, which is this, and then I have placed that object. Okay.
Your trace
Now,
change, index change from h1 to h2.
sorry, it's the same. Yeah. So now this is so this answers your question. You asked me why modular Hamiltonian is modular Hamiltonian. That's the reason. Now physically interpret it. In a physical system, so I had been always harping on the fact S belongs to R, S belongs to R. Right? In real situations, this S will be precisely time. You are going to choose it as time. What you are looking at here is 2-point correlation function of thermal objects, where this A is as if it's Heisenberg evolved by a time S, and then you have operator B. And the fact that the ordering of the operators has changed, it can be achieved by an analytical continuation starting from f of s to f of s minus I. So if you start with this, if you do analytic continuation, you will reach here. And the fact that you can analytically continue and reach it here actually has again far-reaching implications in holography, because this result can be used to prove that you have a bound on quantum chaos. This is the information that goes in. Okay? This is precisely the reason why K is called a Hamiltonian, because if you see here, it's as if the evolution is happening with respect to this kind of an object. Okay? Now, yeah, so I should be done in another, say, 15 minutes. Is that fine?
I'm afraid I'll have to request you to do it in 10 minutes.
Oh, 5 minutes less. Okay. Yes, I can. I think I can. Yeah, I should be able to.
If you want, you can continue again after the short for 15 minutes or so.
So actually, this would be a good point actually then to take a break, and maybe I will maximum go on for another 10 to 15 minutes, even if we, I mean, after the break, if that is.
This f of s minus I and f of s, right? If B was like some product of two things, would it remain B when it comes to the other side, or would the product come?
No, the entire product will come.
Entire product will come.
Yes, yes. No, no.
It's not like trace ka cycle.
No. It is not that.
What do you think? Fine if we take a break now and continue with the discussion after the short one? Fine then, let us take a break.
Okay.
Please thank the speaker.
I am not done yet.
What Sabyasachi means is you are.
Yes, we are good to go.
Yes. So, I have one remark to make about f of z that I did not say when we finished off last time, which is that you see here, this is how ρ1 was defined, e to the power minus k. Now, suppose for a second I am talking about a quantum field theory. I have gone to a QFT. Now that's a continuum. So I am now dealing with infinite dimensional matrices. Now this k is something that is always positive definite, and you can show that it's positive definite, and but that also it creates a problem, that in the sense that it makes this k unbounded, right? The reason you can sort of intuitively see that, so ρ1 we actually did a Smith decomposition and we wrote it in a nice basis, right? We wrote it like this, Ci square, like this. So these objects are precisely the objects that are sitting along the diagonals, right? Now imagine you have an infinite dimensional matrix. So there are objects sitting along the diagonal, but trace of ρ1 has to be 1. That means each of these terms better be infinitesimally small, which means k, I mean e to the power minus lambda 1, e to the power minus lambda 2, these objects that are sitting, the eigenvalues of this matrix k, that must be huge, which makes this is the argument for this k operator being unbounded. Okay? Is that, you seem very confused,
Yeah.
K must be very large.
right?
Oh, right.
Because these things are sitting along the diagonals, but their sum has to be 1.
Right.
But that means each of these has better be very small. But you see, for finite dimension, this f of z, it's entire, because it's a finite dimensional matrix. I can take a bunch of finite quantities and make it 1, right? by entire I mean it's holomorphic over the entire plane. So this is a small remark that I have to say about quantum field theories.
So essentially you meant to say that that is an unbounded.
Yes, K has to be an unbounded for QFT, right? But so this is with, so if that is the case, you see,
So it does not lie in the algebra of the bounded ordinals.
no, it does not. It does not. So you see, by cyclicity, what you need is here in this f of z, you better have this power. So z is some generic complex number, right? So this power must be such that when you take, so I told you that z can also have a time like it can be t plus some I times something complex, right? So this thing better be convergent, and by cyclicity I can bring this here, and this power will be e to the power minus k times 1 minus iz, right? So this part will also have a real part, and this operator also will have a real part. Those two things better be convergent when I take t to infinity, right? Which essentially what I am saying is iz, this basically implies iz and 1 minus iz must have non-negative imaginary parts, right? Huh? What? 1 minus iz. Cyclicity property of trace, you take this here. So this is nothing but e to the power minus k, 1 minus.
Imaginary number and 1 minus that imaginary number have non-negative imaginary parts.
I mean, can we talk about this later? Write z is equal to x plus iy, calculate iz. Okay? What you will see is, so if z is equal to x plus iy, then what you will get is y, from one side you will get y is less than equal to 0 greater than equal to minus 1. Y is imaginary part of z. You just have to do this. Just say that iz, real part of iz will be non-negative. Just impose this condition, you will end up with this.
You wrote imaginary part, that's the condition. Non-negative imaginary parts you wrote, no?
Yeah, non-negative imaginary parts. Z, that is y, yeah, y is the imaginary part of z. Iz, when you multiply with iz, this is a minus y that you get. Then you have e to the power minus iz. So, can we, yeah, this is a really simple computation. I am not saying anything complicated. But what I have showed you is, for a quantum field theory, I did relax the condition and I made it infinite dimensional. I did assume factorizability. Look at what I have got. I have got the same condition for making to ensure that this function better be analytic and nice and well defined. I have got the same strip, right? Without assuming anything like that, I have already derived that imaginary part of z will lie in this region. So this is the small remark that I had to make. Now to set up monotonicity, what you need to do is what I had been calling H1, think of it as a bipartite system. So you have H as HA tensor product HB, and you do your standard trick of purification. So what you have is essentially, so I'm going to use a shorthand. So I have a bipartite system. What I had been calling H1, I'm going to call HA tensor product HB. I'm going to just use HAB for that. And you do your purification. So now you have states psi AB, which basically resides in objects like this. You will also have a phi AB. So this state will be cyclic separating. Phi is anything arbitrary. The same thing, double copy. You can define reduced density matrices rho A associated to the state psi A. You can define sigma A associated to psi B. To phi A, tracing out the B part. And the statement of so this is the statement of monotonicity, okay? Now the only problem here is since I am in a finite dimensional system, so in QFT you had this nice thing. If U is an open set, U tilde is a subset, then A of U tilde was a subalgebra of AU, right? In finite dimension, you have a problem. Suppose I have given you an infinite spin chain. You have chosen 5 qubits. So this algebra is going to act only. So HA, A is suppose the smaller system of 5 qubits. So whatever operator that you act is going to act on this 5 qubit thing, which is typically smaller than your full Hilbert space. So what are you going to do? You then need to define something so that you embed it in the right way, so as if the operators act on states of the full Hilbert space. Okay? So first, what you need to do is ingredient 1, embed algebra. And it's simple to do. The embedding is essentially from the algebra defined on system A to AB. This is pretty obvious to see, right? If you define if you define this kind of an embedding, only the first sector is going to be affected. Only A's are going to be affected. Nothing is going to happen to B. The second thing that you need, the purification we have already done. So because the Hilbert space is typically smaller, the Hilbert space of A is typically smaller than the full Hilbert space HAB, we need to initiate this idea. In some sense, I have to make this claim that as if this smaller Hilbert space should be the operators that act on the smaller Hilbert space should act as if like a subalgebra of the full set of operators that acts on HAB. So for this, the procedure to do, so this is the second ingredient, what you need is isometric embedding. Why isometric? Isometric simply means non-preserving. Isometric, the word is non-preserving. Yeah. So I'm calling this operator U, and what this operator U does is, so it's we have already purified the system. So this is the map that I'm talking about. And if you have this kind of an operator, the definition is, the way it acts is this. Again, this is something which is very intuitive, and you can see why it is defined this way. So obviously, if you associate, you know, this is how you are defining this. So essentially what this tells you is the action, whatever now you act on from your algebra of full AB, it will act on A as if it was acted on by elements picked out from algebra of A only. Okay? So this is what this embedding does. And how is this non-preserving? So if you want to show that, what you need to show is for arbitrary states eta and chi, but again eta is nothing but A of psi, chi is nothing but say B of psi, A and B being two operators. It's very easy to show, and you can see it directly actually from the very definition. Number 3, this is again a 3-4 lines calculation, but what one can show is, if this is what U is, then there is a nice result, which is that U dagger delta psi AB phi AB of U is equal to delta psi A phi A. This is the statement that you can show. And the last thing is, okay, well, when I say you can show this, there are kets sitting everywhere. All these are sandwiched between arbitrary states. And that's how we actually prove this. I'm going to state this theorem. If U is an isometric embedding, then what one has is this inequality. And that is all that we need. So these 4 ingredients basically tells you if you recall, the definition was this. Right? Now, so this is a relation, this is true for any operator x. Okay? The proof of this is there in Witten's notes. It's not at all a complicated proof, it's just time taking, you have to just look through it. And now this, imagine this x operator is delta A. First use this. So, okay, I'm using shorthand. So delta A is delta of psi A given phi A. Okay, psi and phi are fixed. And so this object I'm going to call simply delta AB. Okay, it's obvious from the context what I'm referring to. You take this delta A, plug this here. So what you have is log u dagger delta AB u acting on psi A. Invoke this theorem. Okay? So if you do that, yeah. Sorry. This is log delta F2. Sorry. This should not be here. Delta is log delta A I have replaced with u dagger this. Yeah, sorry. This will be less than equal to this, right? Sorry about the sign here, yeah. So I have to use this, yeah. This will be less than minus delta AB u psi A. Yeah. So essentially I am using this and this. I reach this equation. Okay. X is basically my delta A. Okay. Once I do that, now this action of u, this is how I have defined. So if you put A equal to identity, what you see is u acting on psi A simply gives you psi AB. Okay. So and this is nothing but S of right. So I have taken this dagger out here. This is how I have written it. But u of psi A, if you have put A equal to identity, is nothing but psi AB. So this is sandwiched now between psi AB. This object is nothing but this. There is a less than equal to, which is monotonicity. Okay. The last thing is there are other quantities such as mutual information. So what you can do is, again, you have bipartite system. You define this object sigma AB, which is rho A tensor product rho B, and what you can show is for this particular sigma AB, if you calculate this, this is going to be trace of rho AB log rho AB. So what you do is you take this definition, substitute sigma there, the log is first going to act on rho A times identity, minus log identity minus identity times log of rho b, and if you just simplify it, this is nothing but minus SAB plus SA plus SB. Okay. Now, positivity of relative entropy implied that this object was greater than or equal to 0, which basically means that this object is greater than 0. So what you have is SA plus SB is greater than S of AB. This is known as strong subadditivity. If you have tripartite system, then also what you have, so for tripartite system, you have this kind of inequality. Again, very similar kind of calculations. This essentially tells you SB plus SABC is less than or equal to S of AB plus S of BC. So these are the kind of things that very easily and nicely comes out from this entire construction, and that's it.
So these are the kinds of bounds that.
These are the kind of bounds that you can derive from. It's a very nice sort of, once you have these 4 ingredients in place, you can immediately derive monotonicity. So essentially what this tells you, strong subadditivity is the statement of positivity of relative entropy. Both are equivalent. This is what has come out, right?
Monotonicity under what? Under this isometric embedding. Or should we say?
No. What is your question?
What do you mean monotonicity?
Monotonicity basically tells you that if you have a smaller system, like I mean, yeah, if you have more things, things will be entangled more. So this is
the distance between two states.
What?
Not the entanglement.
No, this is distance between two states rather. Yeah, I should say, yeah, distance between two states. Distinguishability between two states, however you want to put it, distance. Yeah, yeah, it's not right to call it a norm or anything like that.
Yes.
This is not a norm, for sure.
I mean, it's a measure of how separated they are.
How close?
How the words like close and all are used for norm, so that's why let's just call it distinguishable.
Yeah.
Is that fine? Okay.
Isometric embedding, I should think of as some RG or something. Is that
No. Look at isometric embedding. Or isometric embedding, think of it this way. Look at how it look at the action that I have defined.
planting the Hilbert space into a bigger Hilbert space.
I am taking my Hilbert space, planting into a bigger Hilbert space, such that all the operators acting on that bigger Hilbert space acts on it as if the smaller algebra that was already acting on the smaller Hilbert space, I mean both the actions are the same. That is what this embedding does.
You can think of that as some RG kind of thing, you know, when RG also this happens, I guess. You're like flowing into the UV thing and then are you saying the UV states have more entanglement than
No, I won't call this RG at all.
small explain test?
No, I mean it has more it has more similarities to projections than to anything else. But again, U square is not 1, so I won't call it a projection operator, of course. It's an embedding, I mean that's that. I don't think it is right to compare it with RG also. I mean, I don't, this thing has an, so just to give you one counter example, this thing has an inverse.
So U has an inverse.
Yeah. Inverse in the sense like, inverse in the sense of adjoint. If I U dagger will take me things from here to here. So I don't think in RG can you have a mapping the other way. Once you have integrated out high energy modes, you have lost information. I don't think you can get back to, right? RG is inherently a one directional thing. I can't recover back. Once you have given me a IR theory, I can't tell you from which UV theory you came from, right? That's,
No. This is a question of low energy observers and high energy observers, right? You do a low energy measurement, you are in psi. You do more and more high energy measurements, you are into psi AB or something you're going into.
no, I mean it's nothing so complicated as that. All look at the action of it. all that is doing is it is making sure that if I have, see, what is the motivation of doing it? We want to imitate, we want to imitate this kind of a subalgebra structure. Now, for finite dimension, I don't have that. The example of 5 Hilbert spaces that I was giving. You have a spin chain of say 20 spins. You have chosen 5, right? So your Hilbert space will be tensor product of 5 kets on acting on A. Your full Hilbert space will be tensor product of 20 kets, right? How are you going to, so this statement does not naturally hold, because at that point, both AU tilde and AU were acting on the same Hilbert space. Now you can't do that, right? So you need to imitate it in some way, and this is the way to imitate it. You do an embedding. By that, you take this Hilbert space, this smaller one, you define a map such that as if all the operators that were defined on the big thing, whatever it gave, at least in the subspace of the smaller Hilbert space, now this embedding precisely does that. It achieves that purpose. So now you can think of this as some kind of a subalgebra. Now these objects UA together, this operator together, is something like generating your quote unquote subalgebra for you. That is how, that is the picture you should have in mind. Not, I mean, this thing I absolutely do not agree with equivalence with RG. So yeah, that is all.
Was it 15 minutes?
Actually, I finished 5 minutes ago. This was just answered. So. So yeah, from next time onwards, Suchetan will take up, and he will talk about, you'll talk Bisognano Vigna, you will talk, huh?
Half space, Spindler.
Okay, yeah, so he will talk about the simple, the nice systems, 1 plus 1D, QFT. He will integrate half the line and show you guys how null energy, average null energy condition, and he will also do construction, Bisognano Vigna construction, and yeah, and some of these bounds and things like that will come over there also. Thank you.
Please thank Debangshu once.
Can I see your notes once?
Yeah, sure.
Yeah.